Okay, here's Tuesday. We're still in our same clothes. Still on section 4.1, but we're on part 2. So part 2 of section 4.1 and part 2 of kind of the homework becomes a little bit more algebra-y. So if you're an algebra person, an algebra lover, you might like this part a little bit more than the graphing part and kind of toughing out the domain and range questions. So again, we're on this example given that kind of new notation. So we have a function f that assigns each element of its domain x the rule x squared minus 1. And we have a function g, which assigns each member of its domain x the rule 2x plus 1. So if I just real quick change both of those into function notation, f of x equals x squared minus 1. So we have a quadratic function for f, and g of x equals 2x plus 1. And we have a linear function for g. So a little bit more algebra, like I say, and this has a part A through D. So part A, we want to find f of 2, and squashed right next to it is g of 2. So we know in math when things are squashed together, we're thinking about finding the product, we're thinking about multiplication, and really you're just reminding yourself, and this is good for like SAT, which who knows how that's going to go this year, at PSAT. Oh yeah, this means to evaluate f of 2. So in every x I see in my f rule, I want to replace it with a 2. And there's only one x in my f rule. And then I want to multiply that value by whatever I get when I evaluate g of 2. So everywhere I see an x in my g rule, I want to replace it with a 2. And then I want to find the product of those two things. So if I just kind of work vertically down and show my steps, f is our rule x squared minus 1, and I'm replacing the x with 2. So 2 squared minus 1. And I want to multiply, so I'm going to do my dot just to emphasize that I'm multiplying with g of 2, and my rule for g is 2x plus 1. I'm replacing every x I see with a 2. And like I say, since each rule only has one x, it's not too bad. We're just substituting that number in. Really, it's just substitution, right? So we just have to follow our correct order of operations. Exponents happen before subtraction, so 2 squared would be 4. 4 minus 1 will give us 3. Multiplication happens before addition, so we would have 4 plus 1, which gives us 5, and 3 times 5 is 15. And if you're just working vertically down, you don't have to string anything together. This step simplifies to this step, simplifies to this step. You could also find f of 2 and g of 2 kind of individually, and then take those two answers and multiply them together at the end.
Yeah, that's what I was going to say. I'll just show you guys so you don't have to worry about how crazy this can get sometimes, because it can.
Yeah, it can get crazier.
Is just find f of 2 off to the side, and you do all that work. So get 3 there, and then find, this would be g of 2 then. Okay, where you get 2 times 2 plus 1. All right, so you get 5, and then go and plug this in for f of 2, and plug that in for g of 2. I think it's a little bit simpler, but either way definitely works.
Yeah, depends on probably how complicated the original functions that you're given are. Okay, so part B, we're given the notation f of g of 2. Remember, that's how we read that, and that is our composition of functions. And remember that on composition, we work from inside out. So definitely not the only section in the packet where we're going to be talking about composition. So big reminder about composition. This could also be written in other formats. So did you guys remember this, where it looks like fog? But you really read it f open circle of g, and then they might put the 2 on the outside, so you know you're composing f of g of 2. So that would be an equivalent form that means the same thing here. So if I were doing this problem and I want to find f of g of 2, and I know on composition to work from inside out, then I would leave the f on the outside, and I would think, okay, I got to go to my rule for g, and we just did g of 2, right? Mr. Herney showed that work on the side for us, and that gave us the output of 5. And so now I want to evaluate f of 5. So I go to my f rule. Here's my f rule. Wherever there's an x, there's only one x. I'm replacing it with a 5. So I would have 5 squared minus 1. So 25 minus 1, which would give me 24. So there's a little composition. If it's Goff, then you're working g of f of x the other direction, and you always work from inside out. But again, they might have g open circle of f and then whatever value here if they want a numeric answer at the end. So definitely some stuff with numbers for part A and part B. Part C does not have numbers. So we want to find f of x plus 1. So this time there's nothing going on with g, and it's not any different than if it were a number, right? If it were just f of 1, we would go to the f rule. Wherever there is an x, every x we would see, we would replace it with a 1. So the same thing that we do with numbers, the substitution idea we're going to do is just with this whole entire quantity. So f of x plus 1 means go to the f rule. Wherever I see an x, I'm replacing it with the whole thing x plus 1. So if I just work vertically down, here's my f rule. I'm replacing x with the whole quantity x plus 1. I have to square it, and behind that's a minus 1. So my expectation would be that you go ahead and clean this up and kind of get down to that descending order, standard form, expanded form kind of version of your answer. So don't like let the math double possession and think you can just square each part. What are you talking about? No, you write it out twice and we do big distributive property, or we FOIL this out. Don't lose our constant of the negative 1 at the end. So we would get x squared. The outside and the inside would both be a 1x, so they would combine in the middle to give us a 2x. Positive 1 times positive 1 is 1. And now we can lose those parentheses since we FOILed or big distributed that out, and then combine our like terms. And these just happen in this case to cancel. And we get down to the simplified answer, x squared plus 2x. I think a lot of the problems on the homework are definitely like parts like this, like A through E-ish. So make sure that you have the original functions written down in function notation, especially if you start in this crazy notation and you kind of have each set of work and the answer for each.
Yeah, I mean, it's literally the same exact thing. I just think about it a little bit differently. So if I'm plugging x plus 1 into f of x, I like to go up and rewrite f of x as something squared and then minus 1, and then I go in and put x plus 1 in. All right, because sometimes you're going to get maybe like a 3x squared plus 5x, and you're going to be plugging into a couple different spots. That could happen. So that's where I just like
kind of like a placeholder.
Yeah. So it's like, all right, this is where I'm going to plug it in, and then I just go and take the x plus 1 and put it in there.
Okay, so now we're on part D. I will definitely tell you guys that part D you're going to keep seeing over and over in this time of year, and it's definitely something that's going to be tested. So you got to know how to do part D and consistently be getting part D right. So part D, we want to find f of x plus h minus f of x all over h. So again, we're only thinking about our f rule, even though we were given two original functions, f and g. Sometimes we just have to do some sort of function notation stuff for composition with only one of them. So this is not really any different. They kind of like gradually get harder, right? So in that last problem we were saying, oh, if our f rule is something squared minus 1, and it was x plus 1, we were taking that something x plus 1 and plugging it in and squaring it and subtracting 1. Well, the same thing's happening here. F of x plus h means go to the f rule. Wherever there's an x, replace it with x plus h, and there's only one x. So I want to take that x plus h and I want to square it, and then the minus 1 will still be there. So f of x plus h would be x squared, x plus h, the whole thing squared, minus 1. Here's probably the most missed part, the minus f of x. So I don't know how else to like remind you and over exaggerate this, but you're subtracting the original f rule, and your original f rule is more than one term. So you might as well memorize it as minus big brackets. So if you happen to have more than one term, you make sure and distribute that negative through. So this was just the f of x plus h part. We're replacing x with the whole quantity x plus h. This had no x attached to it, that's why it's just a minus 1. We're subtracting big brackets, the original f of x rule, x squared minus 1. And all of that's divided by h. It's really easy to kind of lose that h in the denominator as you're going through the problem because the algebra can get messy on top. So kind of word of caution for that little part about not losing the h in the denominator. There is going to be a pattern that kind of starts consistently happening that hopefully you start to recognize. So as you clean up the top, we're going to square this out, just how we were talking about here, writing out twice, multiplying it out, right? Whether you think FOIL or whether you think big distributive property, we still have the minus 1 on the end. Then I'm going to go ahead and distribute to get rid of that negative sign and clear out my brackets. So it's a negative x squared, and a negative times a negative give me a positive 1. All of that's my numerator, all over h. So as you start getting more and more and more used to these problems, you're going to see a pattern where after you do whatever algebra you need to do, so x times x for the first will give me x squared, The outside would be a xh. The inside would be another xh. You can multiply in either order, which would combine to give me 2xh in the middle, plus h squared. And then I'm just bringing everything else down. So the pattern that's going to consistently happen. So I always tell my kids the pattern. I'd rather you know the pattern, and then if you're not getting the pattern to happen, most likely you forgot to distribute the negative. Okay? Is that everything except things with h's should cancel. So if you're not getting things that are constants to cancel, if you're not getting terms with x's only to cancel, then you screwed up. Everything should be canceling except things with h's at the end, typically. I think most of the time. Now I'm like second guessing myself, but definitely you should get some things to cancel. And then in this problem, there's lots of ways to do it, but you might notice that there's an h between all three of these. So if you factor the h from the top, h times the quantity 2x plus h. Remember when we pull out a GCF, we're just undoing the distributive property. And now these h's can reduce out because we're in factored form and we can cancel those common factors. And we get the expression 2x plus h. So don't be surprised if you get an expression with x's and h's as your final answer. Sometimes you might just get something as a constant as your final answer. But you should have some patterns that are going on where some things cancel except things that have h's towards the end. Okay? So we're going to erase this one, and I'm going to do another one similar to. And then Hernie's going to do a crazy one with fractions that has just this kind of part. And then a last little bit of graphing to match the last little part. So we're going to have like kind of a part A, B, C. And we have different original functions.
I'm erasing real good.
Here, this one's the one that's a little wet. Okay. There we go. All right, so this time we're starting in function notation, and we're given f of x equals 3x plus 7, so another linear function, and g of x equals x minus 2, the whole entire quantity squared. So a quadratic function, but just left as x minus 2, the whole thing squared, instead of all the way FOILed out in expanded form. So for part A, we want to find f open circle of g of x, which you guys will say is fog. It's the same thing as f of g of x, but this time we're not evaluating a specific number, right? So it's still composition. We still work from inside out. We're just not doing anything with a number. So if I leave the f on the outside and I don't have a number here, it's just g of x, you can think, oh, take every x you see in the g rule and replace it with x. It's just not going to change anything. Or what is the original g of x rule? Oh, it's x minus 2, the whole thing squared. Right? So I'm just replacing that g of x with what that original rule was that was given to me. And now I want to find f of x minus 2, the whole thing squared. So if we kind of like use Tony's idea, our f of x rule was 3 times x plus 7. There's only one x, so I have to have 3 times something plus 7. So the 3 times something, oh, this is that something, x minus 2, the whole thing squared. So my expectation would be, okay, now clean that up a little bit. So instead of leaving it as, hey, a whole quantity squared with a 3 that's multiplied in front, exponents have in first, let's square this out. Let's take this binomial and square it out, which is going to give us a trinomial answer. Let's distribute the 3, and let's not lose our plus 7, see if we have any like terms on the end. So if you need brackets, maybe instead of parentheses to overemphasize that we're doing the exponents first. So x minus 2 times itself, x minus 2, wouldn't that give me x squared? I'd have a negative 2x, another negative 2x, which could combine in the middle to give me negative 4 of it, negative 4x, and negative 4 times negative, or negative 2 times negative 2 is positive 4. Whoa. Getting all tongue-tied. And then we're going to distribute our 3 through. So 3x squared minus 12x plus 12 plus 7. And we can combine our little constants right here for a last little bit of like terms. And we have 3x squared minus 12x plus 19. It is equivalent up here. They are really the same version of each other. One's just kind of more in standard form descending order, and one's kind of just the expression left more in like transformation form if we were thinking about graphing. Okay, but I would think more on a PSAT, SAT kind of question, they would clean it up to here. So you need to practice that skill too. So same original rules, but part B, we want to find G of F of 5. So probably a little easier when you have that number value instead of when it's left in terms of X. Remember, this could be written as G open circle of F of 5. We're thinking Goff instead of fog.
Remember, guys, try to do this on your own first. Don't just watch the whole time.
Yeah.
Like, you should have a pretty good idea of what you're doing. See if you can do it on your own. Pause the video.
Yeah, especially this type, right? The new stuff with the f of x plus h minus f of x all over h, that part maybe you need to get a little bit more guidance and see a few more of them, but by the end you should be okay with those too. Your dad would be okay with them on your homework. So composition, if we're working from inside out, our inside this time is f of 5. So if you want to go and do a little scratch work to evaluate f of 5 first, that's fine. You only have one x to replace with this and substitute the 5 into. So we would get 15 plus 7. Those would add together and give us what, 22? Or you could show that work here. It just depends on your comfort level. So f of 5 turned into the output 22. And now we're trying to find g of 22. So I go to my g rule. There's only one x in my g rule. Wherever that x is, I'm replacing it with the numerical value 22. Order of operations, we start inside parentheses. So 22 minus 2 would give us 20. And 20 squared, maybe you know, maybe you don't, is 400. Perfect square. So a lot less work when it's a number value than left in terms of x. Okay, so like we did before, we're going to do that last part. So f of x plus h is part C minus f of x all over h. Remember, we're going to see this one a few times. Don't skip these on the homework. Don't just copy off of the website. You need to know how to do them on your own. So this time I only have stuff going on with my rule for f. So I'm kind of ignoring my rule for g, and I'm going to my linear function f. Okay, so f of x plus h means go to the f rule. Wherever there's an x, put the whole quantity x plus h, just as if it were a number, just as if it were the whole stuff here where we're replacing all of this in place of the x. Right? So if I go to my f rule, I have a 3. I'm replacing x with the whole thing x plus h. There's no exponent attached to the x. That's all I got. I still have the plus 7 behind it. And then minus big brackets. Now we have to subtract all of f of x, meaning the original f of x rule. And the original f of x rule is more than one term. If you have more than one term, you got to distribute that negative through. So just memorize minus big brackets. Substitute your original f of x rule in, and then worry about cleaning it up. And don't forget about all divided by h at the bottom, right? Like we said. So we're going to expect some patterns like we had kind of going on last time. If you follow the appropriate algebra and you're doing this kind of piece right, which you'll see a lot of this chunk again in calculus, then you'll start seeing those patterns. And if you're not seeing the pattern, then you know you kind of made some mistake. And to go back and find it, that's the goal, right? Because you're in pre-calc. You've got to be able to go back and start finding your own mistakes. So I'm going to distribute my 3 through. So 3x plus 3h plus 7. Distribute my negative through. Minus 3x minus 7. All divided by h. And I said, oh, remember, some things should cancel, except things with h's. Oh, look at this. Positive 7, negative 7. They cancel. Negative 3x, positive 3x. Those are opposites. They're going to cancel. Now I have things that only involve h. It's actually even a little easier than last time. I don't even need to really think about factoring out a GCF. It's a single term over a single term, and they have a common factor of h that I can immediately cancel out, slice out, and get 3. So that one, we didn't get a final expression with x's and h's. We just got a constant value. Okay? So that was part ABC from those two original functions. So we're going to switch our rule. I'll erase while Hermie kind of gets ready to show you a nasty one. So he needs more board space.
Hey guys, one thing to remember, make sure you're writing the h in your denominator every single time. Sometimes you get lazy and like to not write that and throw it back in at the end, or sometimes you totally forget it. Just make sure you're writing that every time.
All right.
All right, so this time we're going to do f of x equals, I'm going to give you 5 over x. Okay, we're going to have to find f of x plus h minus f of x, all divided by h. All right, so same thing as before, but now you're just dealing with a fraction, and fractions are fun. So I'm first going to figure out what is f of x plus h. So all I'm doing is plugging x plus h into my function wherever I see my x. Okay, so that was really just 5 divided by something, and that something is going to be the x plus h. Minus f of x, well, we just copied that function down. F of x was 5 over x. And this is now all divided by h. All right, so now we got fractions within a fraction. So what you're going to want to do is just get one fraction on top, one fraction on bottom, and then copy dot flip. All right, so to get one fraction on top, we need a common denominator. To get a common denominator, I'm going to multiply this guy by x over x, and this one by x plus h over x plus h. All right, so now when I do that, over here, I've got 5x all over x times x plus h. All right, I'm not going to multiply that through just because I've done enough of these problems and know better. Over here, one tricky thing is this is negative 5. I'm going to distribute that to everything on top here. So it's going to be negative 5x minus 5h. All divided by x times x plus h, which is then all divided by h. All right, now on top I got one denominator, so I can combine my fractions. All right, where I've got 5x minus 5x minus 5h, all divided by x times x plus h, all over h. And I'm going to write that as h over 1. Okay, because now I got to my goal where I get one fraction on top, one fraction on bottom. We can do a little copy dot flip. All right. I do notice that my 5x will cancel my negative 5x. So I'll make my life a little bit easier here. So now I've got negative 5h over x times x plus h. Okay, now it's a little bit of copy, a little bit of dot, a little bit of flip. There we go. All right, so you can combine this as one fraction here if you wanted to. If you notice, this h is being multiplied by everything else on top. It's h times negative 5 times 1. This h on bottom is being multiplied by x plus h, so it's times everything. So if it's being multiplied by everything on top, being multiplied by everything on bottom, you can cancel that. All right, bringing me to my answer of negative 5 over x times x plus h. Are you right if they don't multiply it out?
Yeah.
Yeah.
Definitely leave the denominator in factored form.
Okay.
Yep.
And there we go. So it's that same f of x plus h minus f of x all over h. You guys will probably be seeing this later this week, and it will be showing up pretty much all next week too. So the sooner you figure this out, the better off you're going to be. We're going to stop doing those now, and I want to go back to some graphing because I love to graph so much. All right, these are going to be a little bit trickier of graphs. And as long as we were talking about domain and range yesterday, we're going to still talk about some more domain and range. So I want you to graph this. See if you guys can graph these without any help. We got this weird notation again, which is fine. Quit being big babies. All right. So see if you guys can graph that. All right, so the first thing we're going to do when we graph this is I'd say equals. I would factor the top and see what happens. X plus 1 times x minus 1 all over x minus 1. And wouldn't you know that the x minus 1's cancel? All right, which means my graph is going to look pretty much like x plus 1. We graph x plus 1. This is just linear. If you're thinking the equation y equals x plus 1, I have a slope of 1. My y-intercept's also 1. So you go up 1 over 1, up 1 over 1, up 1 over 1. Just like that. Okay? However, it's not quite the same as this function here, because this function, we can't divide by 1. Or when x is 1, because then we're dividing by 0. So really what this is a point disco at x equals 1. All right, because that canceled. So to find the y value of our point disco, you plug x equals 1, or whatever your value is here, back into whatever is remaining, which is x plus 1. So our y value is going to be 1 plus 1, which is 2. So our point disco is actually going to be happening at 1, 2. Which makes a lot of sense because that would have been a point on this graph. All right, well, we still want you guys to do domain and range on this. So my domain is going to be all my x values. Okay. You could go back to finding this algebraically, right? We don't have any logarithms. We don't have any square roots. We do have a denominator. I would set that denominator not equal to 0, which means x does not equal 1, which if you were to do that on a number line, you would be including everything except for 1. All right, which makes a lot of sense when you actually go ahead and graph this, because here is our only point that we don't have for an x value at x equals 1. So my domain is going to be x equals negative infinity to 1. All right, union 1 to infinity. All right, now the range, like I said, you have to be able to graph it to know what the range is. We have our graph here. If you guys look, this graph goes down forever. It also goes up forever. The only thing that we are missing here is that y value, right? We never have a y value at that spot, which is y equals 2. So for my range, I'm going to get y equals, I go from negative infinity all the way up to 2. And then I pick up that 2 and go up to infinity, and then that's it. All right. That one wasn't so bad. Sweet. So let's do another one. Guys, our next graph, I'll erase this. You can start thinking about it. Is going to be g. We're going to get x to the 4th over x squared. All right. So I'll go ahead and see if you guys can figure out how to graph that, what it's going to look like. Is there going to be any point discos, all that fun jazz. All right, so this does cancel, right? I'm going to be left with, let's write g of x. All right, it's essentially going to be the same thing as x squared as long as x does not equal 0. Because if x was 0, that would have been a point disco. Versus here, x is okay to equal 0. All right, x squared is just going to be the graph of a parabola. We have a point disco at x equals 0 because we set the denominator equal to 0 and solve it. X squared cannot equal 0, so we have a point disco at x equals 0. plug that back into our whatever's left over. My y value is going to be 0 squared, which is also 0. So our point disco is at the 0 count of 0.
So one thing about some of these is, at first glance, you might be like, I have no idea what this is going to graph. This doesn't look like anything we've graphed before, like a transformation of a parent function. But the idea is when you get that factoring to happen and some nice stuff cancels, then the graph is behaving like a graph you recognize with just some special spot. So that's what I always say, like the graph behaves like the g of x equals x squared graph, but with that point disco at 0, 0.
All right, so let's talk about domain and range again. Our domain, guys, once again, you can find this algebraically if you really wanted to. All right, no logarithms, no square roots, but we do have a denominator. You set your denominator not equal to 0. X cannot equal 0 then. All right, which means it's going to be all of our other values. X equals negative infinity all the way up to 0, union 0 to infinity. Okay, range is a little bit weird on this. Our range goes all the way up forever and ever and ever, right? Okay, it goes all the way down to 0, but it doesn't actually get to 0 because we have a point disco there. It gets basically as close as you can get to 0 without getting to 0. So when I talk about my range, it's going to be y equals 0 to infinity, but we're not actually going to include 0 in this one. Okay. If we did have a point there, now you would include 0 and it would go to infinity, but we don't. So that's why we're going to have it open. All right. So next problem, one last one. You guys love rational functions, I know. All right, last one is, let's just go back to normal notation. Equals negative 3 over x. Okay, as a rational function, you guys should know how to graph this. It's just actually super easy. We don't have a point disco here because we don't have stuff that cancels on top and on bottom. Okay, think about your rational functions, what we know about them. My degree is bigger on the bottom, so it means I have a vertical asymptote, or I'm sorry, horizontal asymptote at 0, since my degree is bigger on bottom. All right, because that's really like x is 0 up on top. All right, we have a vertical asymptote at 0 because I set my denominator equal to 0. Vertical asymptote at 0. I do not have any x-intercepts. All right, I set the top, the numerator, equal to 0 and solve for x to find my x-intercepts. There's nothing there. Also for y-intercepts, we don't have a y-intercept as a vertical asymptote on our y-axis. All right, also we would normally set x equal to 0. We get negative 3 over 0. Can't divide by 0, so that'd be undefined for our y-intercept. You guys can always go back to sign analysis to figure out, are we going to be on the top part or the bottom part? So when I figure this out, let's plug in any number bigger than 0, really. Let's say x equals 3. Plug 3 in, you get negative 3 divided by 3. Is going to give you a negative 1. All right, so if x is 3, y is going to be negative 1. Are we going to be on the top part or are we going to be on the bottom part? We are going to be on the bottom part there. Okay, you could plug in a value over here as well to figure out, are we going to be on top or on the bottom? Oops, on top or on the bottom. But you could also think about multiplicity. Okay, that vertical asymptote is only going to occur once. So we're going to stay on the bottom or is it going to go up top? Well, since it only occurs once, an odd number of times, it's going to switch. And that's what your graph is going to look like. All right. So just got to talk about domain and range one last time. For domain, all right, it's really every x value except for x equals 0. Once again, think about logarithms, square roots, and denominators. Set your denominator not equal to 0. So we're going to get negative infinity all the way up to 0, union 0 to infinity. Okay. Our range is going to be pretty much the same thing. Okay, we got every y value going down forever and ever. It goes all the way up to 0, but we don't actually have a value on here. Okay. And then it starts again right after 0 and goes up forever. So for our range, we're going to get y equals negative infinity to 0, union 0 to infinity. Just like that. All right. So it's just all rational. It's back to rational functions, point discontinuities, try to factor stuff, see if it cancels. And that's really going to be about it.